Okay. So apologies for Monday. I was somewhat sick. So today we're going to do this, probably the last topic of the course. It's a very beautiful, fairly recently developed technique. Perhaps its origins were in the 90s, then it started being used more in the 2000s, and the last 10 years or something it's become a very, very popular and useful tool. So anyway, it's called dependent random choice, and I'll try and talk about what it is. So, so remember when we were looking for a copy of K4, when we were proving Szemeredi's bound on the Ramsey-Turan number of K4, what did we do? We had two sets. We call them A and B. What we knew was that if you threw away a few elements here, next door. If we threw away a few elements, then every other pair of elements had many vertices in common. Right? Because if you threw away vertices with a degree less than half plus delta, any other pair has common neighborhood like delta times n. Right? Delta times the size of this set. Right? That was what we used. What we said was, let's apply that to a pair that's an edge, find a large common neighborhood. Then inside here, we just have to find one more edge. We have our K4. Okay, so the idea is, it's very useful to find a large set A such that every pair of vertices has large common neighborhood. Okay, does that make sense? So what we wanted here was A should be big and for every pair U, V, and A, the neighborhood of U intersect the neighborhood of V was big. Okay, that was the property that we used to find these K4s, under the assumption the independence number is small. Right? So let's try and prove a general form of that. And what was the motivating example? What do we want to prove? We want to prove the following theorem of Sudakov. It says that the Ramsey-Turan number K4 n to the 1 minus epsilon is little o n squared. Right? Remember that the Ramsey-Turan number n K4 little o n was n squared over 8, plus little o n squared. Right? So if your restriction on the independence number is just that its size little o n, there exist examples which have many edges, n squared over 8 edges. This theorem says if you restrict the independence number more, make it as small as this, then there are no such examples. Okay? So what do we want? What do we want? Motivated by the picture over there. Or perhaps I should say, so let G be a graph with epsilon n squared edges and no independent set larger than n to the 2 minus epsilon, n to the 1 minus epsilon.
We have to prove that doesn't have a K4.
You've got to prove that it does have a K4. Yeah. Okay, so what do you want, how do you want to find this K4? Motivated by what I drew over there.
We need to find a part A.
Yeah. So a subset of the vertex set, which is large. What do you mean by large? Yeah. Such that where large means what, and for all uv in A, n of u intersect n of v should be at least, yeah, the power 1 minus upside. Right. Right. Okay, let's try and prove that lemma. Sorry, step back a second. So you should perhaps ignore this for now. There's going to be some condition on G that if I tell you now it's going to look very confusing, but let's do the proof and we'll see what the condition is. So under some condition that I'm telling you is going to involve some T, there exists a subset of the vertices such that A has at least A elements, and all subsets of A of size S, the intersection of the neighbourhood of U, such that U is in S, has size at least R. I'm going to turn this around to make it easy to understand. Oops. R for all subsets of A of size S. Okay, so we're going to ask not only, so if S is 2, it's just saying every pair of vertices, their common neighbourhood is size at least R. Right? That's just a general version of what we want here. Does it make sense? Does it make sense or not? There's a condition I haven't told you. There has to be some condition, otherwise the graph could be empty. Right? But the condition will be a little bit complicated. It'll be just exactly what comes out of the proof. Okay? But does the statement make sense? You all look confused. This is despite the fact I took out the confusing part. Is it okay or not? Questions? So for any A, for any R, for any S, some condition will allow us to find a set of size at least A, such all S subsets have common neighbourhood at least R. Right? Okay. Proof. Suggestions. how can we possibly find, so this condition is going to be some lower bound on the number of edges, right? It's going to look a bit complicated, but it's basically going to be number of edges of G is at least something. So suppose you've got a graph and you know the number of edges is at least something, some function of A, R, and S. How could you possibly go about finding a set with this property? Well, give me an incorrect answer that you might think of. Right? Yeah, so one thing might be to try and construct it, to try and like say, okay, here's a vertex, that one's good. Okay, here's one that has lots of neighbors with it. It's going to go greedily until we get stuck. Okay, that's one approach.
To find something with minimum degree.
Right, so try and find a subgraph with minimum degree and make the minimum degree so large, things are forced to have very... Yes, that would work, but it would give a very weak... it would give a strong assumption. You'd need many, many edges to do that. And remember, we're going to be working with these graphs which are very sparse. So the minimum degree we could hope for would only be epsilon times n. So we can't hope to have a big enough minimum degree to force it. Yeah, so that would work, but I want something better. You could try applying Szemeredi, but once again, because we're dealing with sparse graphs, the Szemeredi partition is all the pairs will be sparse. So that also won't work. Yeah, a random, so it's not, you're given the graph, right? A random A, right? There we go. Now we're getting somewhere. Let's try and take a random A. But what's our random A going to have? So if we just pick A sort of uniformly at random, well, once again, our graph is sparse. So how are we going to force pairs of vertices to have large intersection, their neighbors who intersect? Right? They might just not intersect. I mean, you might have like a bipartite graph, and you pick randomly, you get half from either side. And then the neighborhoods of points on the opposite sides, right? So your graph might be, your graph might be bipartite, right? It might be a subgraph of this. If you pick A randomly, you'll probably get some here and some here. And then these guys have no common neighbors. So it turns out that random doesn't work if you just pick uniformly at random. What we want to do is we want to pick a probability distribution on the vertices and pick randomly according to that in some clever way. And this probability distribution should depend on the graph, which is why it's called dependent random choice. We're going to pick randomly, but depending on the graph G. Because somehow this has to encode, this random choice has to encode the structure of our graph. Now that sounds very complicated. It sounds quite scary, right? We're going to pick some crazy distribution on the subsets of size S. So let's try and think of a very simple way you could do that. Or sorry, sets of size A. Right? What's a very simple way in which you could pick, in some way randomly, a set A that makes the elements more likely to have common neighbors? So in particular, how could you guarantee they have at least one common neighbor? How could you pick a subset of vertices randomly that's pretty big, and that you guarantee that they have a common neighbor? Yeah, I mean, whatever, just say.
You can pick between the neighbors of the vertex.
Yeah, so right, if you pick a vertex randomly and look at its neighborhood, how large is this neighborhood? Well, on average, it's the average degree of a vertex, right? So in the situation we're dealing with, it would have like epsilon n elements. So it's big. And every pair of vertices here have a common neighbor. In fact, more. all of them have a common neighbor, this guy. Right? So this is a very simple way of picking a large set where every subset has at least one common neighbor. Okay, so what's the idea? Well, perhaps you can guess. So that's not enough. Yeah. Exactly. So that's exactly what we're going to do. Instead of picking one vertex, we're going to pick a bunch of vertices, T. And we're going to look at the common neighborhood of T. I'm going to write n of T. So this possibly conflicts with some notation at some other part of the course. So apologies for that. It's just very useful. This today is the intersection over vertices in T of the neighborhood of U. Okay, so n of T is today going to be this intersection of neighborhoods. Okay, and this is our first attempt at A. So it turns out this won't be exactly our A, but it's our first attempt, right? So as often with the probabilistic method, you pick randomly, it doesn't give you exactly what you want, then you can mess around with it later and fix it. Okay, so let's do this more carefully. So let V1 up to Vt one second. So let them be chosen. Is that right? Ah, thank you. Yeah, but the construction's okay. Sorry? Não tem que ser. Okay. Is that right? Image? From image. Ah, yeah? Okay. Ah, yeah, okay. True. Right? No. No? Okay. Right. So you choose the vertices one by one, uniformly at random, and independently, yeah. This word, I always, in the middle of it, assume I've gone, I'm going on for too long. Is that right? Yeah, okay. This word goes on for way too long. Okay, so you pick them, V1 up to Vt. Each one, just pick it uniformly from all the vertices. Okay, and then put it back in the bag, and then pick again. So the V's can be the same. So we can pick with repetition. Then we just set T to be the set V1 up to Vt. Okay? So it doesn't really matter that we're picking them with repetition. It just makes the calculation slightly cleaner. Okay? So this is a set of size at most t. It might be smaller. Okay, and then let's set x to be the size of this common neighborhood of t. And let's calculate the expected value of x. Okay, so what is the expected value of x? Yeah. Right, so it's the sum over vertices in G of the probability that v is in n of t. Right? Which is the same thing as in neighborhood of v1 intersection neighborhood of vt. Right? So here's v. V has to be in the neighborhood of all of these random vertices. So maybe I'll call it u just to distinguish from the vi's. What is that probability? Right, so it's not a random graph. It's not a random graph. Thank you. Excellent. U being in the neighborhood of t is the same thing as t being a subset of the neighborhood of u. So each of these vertices has to be chosen in the neighborhood of u. And they're all chosen independently and uniformly, so this probability is equal to this is to if and only if t is contained in the neighborhood of u. Right? U is in the common neighborhood of t if and only if t is in the neighborhood of u. Right. So what's the probability that vi is in the neighborhood of u? Yeah, du over n. Right. Exactly d over n. That's true for each of these guys. There are t of them. They're all independent. So it's exactly d of u over n to the t. Right? It's OK? Just each of them has to be chosen in the neighborhood. That's probability exactly d of u over n. And this thing is at least what? Yeah, just by convexity, this is at least n times sum of d of u over n to the t, right? If they're all the terms are equal, so you minimize something, this is convexity. So Jensen, whatever. OK, this is twice number of edges over n. OK, so we have a lower bound on the expected size of x. Right? OK. So we want x to be big, right? We want set A, our final set, to be big. But we also want there not to be any subsets of size s that have small common neighborhood. So what happens if some subset of this set has small common neighborhood? Well, we'd like there to be none. So OK, maybe just the expected number is smaller than 1, in which case we're happy. So let's calculate the expected number. Back over here. Yeah. Right, so yeah, so good question. So you're right. So it's not immediate that the expected size of this thing is small that we're done, but then we'll see. We'll do a trick at the end. I mean, we haven't said what this is yet. Yeah, so it's a good question. Anyway, it's a natural thing to calculate, is to find y to be what? The number of, what would you like to count? Yeah, the bad things, right? Subsets of n of t, size s, n of s is less than r. Right? These are the bad things, the bad s sets. So what's the expected value of y? And we want this to be small, right? Let's put, okay, we're equal for starters.
This is even worse than the condition we want, right? Because we want the intersection of all such passes to be greater than r.
This is just the complement, right? N of s is exactly this thing. This is n of s.
Ah, yes.
Yeah. Right. Okay. So, what is the expected value of y? Well, it's the sum over things of the probability that that thing occurs. So let me write it down. It's the sum over subsets of the vertex set of size s. So the probability that s is contained in n of t and the neighborhood of s is less than r. Is that right? Aha. So you want to do this instead. Okay. So now tell me why that's the wrong thing to do. What I'd written needed correcting, but that was the wrong way to correct it. So tell me why. So why have what I written has what I written not really make sense? That doesn't really make sense as it's written now. T is random, right? So it's a bit silly to sum over subsets of a random set. And how about this thing? Is this random? No, it's got nothing to do with t, right? This is deterministic and this is random. So we should swap them. So in fact, this should go here. And this is sum over all things of size s, such that the neighborhood of s is less than r. Right? Now, what is this event equivalent to? Exactly. Right? S is contained in the common neighborhood of t is the same thing as t is contained in the common neighborhood of s. Right? Just by the same observation as before. And what's the probability of this? Uh-huh. Right. Very good. So this is doing two steps. So the first step is each of these guys has to be contained in n of s. So it's exactly size of n of s over n to the power t. Summing of s with these properties. But one of the properties is that n of s is at most r. So this in particular is less than n choose s times r over n to the t. Right? It's okay? Okay, so we're almost done. So let's just record here what we've proved. So the expectation of x is at least this. N 2e of g over n squared to the t. The expectation of y is at most that thing, n choose s, r over n to the t. Now, how are you going to deduce that there exists a set A with the properties you want, and what's the condition that you need? So perhaps I'll tell you the condition, just give you a hint. It's quite a big hint. I'll give you another minute before I give you the big hint. So you know that if you pick randomly, the expected size of your common neighborhood is this. So you pick this t randomly, and you look at this common neighborhood. And you see that the expected size is big. And the expected number of bad S sets is small. But OK, you don't know how many there are. Maybe this is still a big number. Well, we want to have none. How are we going to get from few to none?
Maybe we throw away somewhere.
Yeah, exactly. How do we always do it? We pick one vertex from each and throw it out. So let's throw out exactly y vertices. Okay? One from each set S, or most y. That's a random number, right? This is a random set. This is a random number. I would like it to be true that the remaining set has size at least A. If the remaining set has size at least A, then we're happy. And I just want there to be a single choice of t such that that works. Right? So all I want is that the expected size of A is, the expected size of this set is at least A. And what can you tell me about the expected size of this set?
It's larger than the expectation of x minus the expectation.
Exactly. The size of this set is x minus y. I mean, at least x minus y, fewer. So as long as the expectation of x minus the expectation of y is at least A, you're happy by linearity. The condition is exactly that. N times 2e of g over n squared to the t minus n choose s r over n to the t is at least A. Right? Which is exactly what you need to make the argument work.
So sorry, but
Yeah.
if the expectation is bigger than y, then we have that the at least one.
So if the expectation of x minus y, right? Remember the expectation of x minus y.
So it exists, right?
Yeah, exactly. But
That's it.
yeah. So this condition says that the expectation of x minus y is at least a. So there must exist a t such that x minus y is at least a. Take that t and remove one vertex from each bad S set. Should I write that down? Let me write it down, just in case. Right. Implies that, so I'll write star for this. So G. Star implies the expectation of x minus y, which equals the expectation of x minus the expectation of y, is at least a. Right? Which implies that there exists t such that x minus y is at least a. Right? X and y are functions of t. Right? This is x of t and y of t. Now just remove one vertex from each subset of n of t. So take this t. For each subset of n of t of size s, whose intersection is at most r. There are y such sets, so you remove at most y vertices, so you're left with at least a. The remaining set is a.
Why removing one from each will end your problem?
So
Because the neighborhood is
Yeah.
less than r, right? The size of the neighborhood is less.
right. So suppose, yeah. So here's your neighborhood of t. Here I've removed one vertex from each bad S set, and I claim there's no bad S sets left in here. So I take an S set. Is it bad? Well, no, because I removed one vertex from each. So every bad one has at least one vertex here. Right?
The size of the sex of the set is fixed.
The size that is S. So I'm trying to show that every S set, yeah, is good. So if there's a bad one, it must have a vertex here. So I need to remove put one vertex of each here. And maybe I can use the same vertex many times, but maybe not. Okay? Okay, so we've proved the dependent random choice lemma. Now we have more than an hour, so let's give lots of applications. So first, why have we already proved the theorem of Sudakov? So we wanted a set with these properties. So we want to apply the lemma to our graph. So we just need to pick A, R, S, and T. So what are A, R, S, and T? Very good. So let's write out the inequality in C, right? Yeah. So what is this? What do we want? We want n times, what's E of G? E of G is epsilon n squared. So 2 epsilon to the t minus n choose 2 times n to the minus epsilon t should be at least n to the 1 minus epsilon. So tell me what to take t to be. Perhaps the hint is you have a very wide range of possibilities here. Things should be bigger than that, I think. So why does it? So yeah, suppose you want to take t to be 1,000. Is that what you said? So what do we get? Here we get n times a constant. Here we get n squared times n to the minus 1,000 epsilon. But epsilon is 10 to the minus 100. This is basically n squared. So you get n minus n squared, which is negative. OK, so that's no good. It needs to be bigger than that.
1 over epsilon.
Now we're getting closer. Now we have n times some tiny constant minus n squared times 1 over n. So it's tiny constant times n minus n, still negative.
1 over epsilon squared.
Yeah, I mean, 2 over epsilon's enough, right? Right, like 2 over epsilon, suddenly this is 1 over n squared, this is constant, and you have constant times n minus constant. So you win easily. Okay. So in fact, the best choice, so suppose we now will let epsilon tend to 0, then we could take, what am I saying? So this breaks when epsilon to the 1 over epsilon is smaller than n to the minus epsilon. Right? So we want, the only condition we needed, right, we put t as 2 over epsilon. This is now constant. This is crazy constant times n. And that should beat n to the 1 minus epsilon. Cancel n, and you get basically epsilon, so really, okay, 2 epsilon to the 2 over epsilon should be bigger than n to the minus epsilon. Which is basically saying epsilon should be at least e to the minus root log n or something. I should take logs, right? Let me take logs and see. 2 over epsilon log 1 over epsilon, let me forget the 2, is bigger than epsilon log n. Epsilon squared. Log 1 is basically log n, so they're basically, what? Doesn't make any sense. Sorry, log 1, so this is like a log. So 1 over epsilon is basically root log n. What? Ah, maybe that's right. Sorry, maybe that's right. With a log. Log n. Anyway, it doesn't matter, right? So you can get some kind of yeah. So if you want to put here, you could get a stronger bound of this, but this is low, and you can also get a stronger one here. This thing can also go to 0 in some way. And this gives a sort of roughly, is it optimal? I'm not sure if it's optimal. But anyway, if you want to, you can prove something stronger. OK. Now, here's another application.
Sorry,
Yeah, please.
isn't that a problem? Because I can't epsilon to 0.
Why not?
Because it can be
Epsilon is, sorry?
it can be lower than n to the power.
Ah, so,
Why are they two epsilons are the same as epsilon.
Yeah, they don't need to be. They don't need to be. Yeah. Sorry, so I think that the correct version of this theorem is something like e to the minus root log n times n is at most e to the minus root log n times n squared. Something like that. Right, so you don't need this to go all the way down, and you don't need this, but it turns out that, so there's some trade-off between the two, I guess. Right. Yeah, I just the convenience of not having more letters, but yeah, so suppose I put in here a delta n squared, and you said, what is delta? Well, yeah, sorry, so you need this. That's right.
I think that one, the exponent, it's an epsilon.
Thank you. Very good. Good. Right. So if delta is a constant, then epsilon can basically be 1 over root log n. But if epsilon is constant, then delta can be basically n to some very small power. Yeah. So there's some, yeah, exactly. Some trade-off, and it's given by exactly this inequality. Yeah, thank you. That's better. Does that make sense? Sorry, you had.
I am confused.
So this is true for every fixed epsilon and delta if n tends to infinity. Right? So in particular, it's true if epsilon and delta tend to 0 very slowly with n. Right? So if epsilon is 1 over log 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 n and delta is 1 over log 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 n, then it's true. But if they tend to 0 too fast, then it's going to break. And at that point, the proof breaks. So that's fine for proving what we wanted to prove. We just wanted to prove little o n squared, which just means that the density does tend to 0, at some rate, maybe a slow rate. So we proved it's at most n squared over log 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 n or something. But actually, we proved something stronger. We proved it's basically, what this tells you is that really it's much smaller than that. So it's whatever this delta is, basically n to the minus epsilon squared. So we prove something like n to the 2 minus epsilon squared.
But is that delta n squared is proving little of n squared?
Yeah, because delta is tending to 0 slowly.
So delta depends on n.
So this is it's a good point. So we should discuss it. So I will always talk about deltas and epsilons as if they're constants. However, they're arbitrary positive constants. They can be as small as you like. So another way of thinking about it is to think about them tending to 0 slowly as n tends to infinity. There are two basically equivalent ways of thinking about the problem. Depends whether you like to think about n just being some fixed large number, or like to think about m being a sequence of numbers tending to infinity. Right? So I will jump back and forth between these two perspectives, and so I apologize if that's confusing. You should pick whichever perspective you prefer. Right? Whether you want to think of delta as an arbitrarily small constant or as a function tending to 0 slowly, it's equivalent. Okay. So when I jump back and forth, yeah, please don't get confused. So this is what's going on. Okay. Does that make sense? Okay. Okay. Right. Okay. This is like 3 or something. Okay. So recall that the extremal number of a complete bipartite graph KST is a most what? almost 2 minus 1 over s. Yeah. Right. So this is a generalization of this theorem. So let H be a bipartite graph with a vertex set, let's call the vertex set x union y. Such that, so what's the property? The neighborhood of a vertex in X is at most S. So send the most S edges to, well, okay. Excuse me. The degree of U is at most S for every U in X. Okay? So this would be true for this graph. Every vertex in the side with T elements has degree S. Right? And the conclusion is the same. The extremal number of H is at most some constant depending on H times n to the 2 minus 1 over S. No, it's bipartite. Sorry. So when I say it's bipartite and write this, I mean this is the bipartition. So all edges go between x and y, and every vertex in X has degree at most S. Which other one? Neighborhood of U intersect Y? Oh, sorry. Right, so that's a special case of this. So in particular, KST satisfies this property, and therefore, and this holds. So this generalizes that theorem. Right? This holds not only for KST, but for any bipartite graph with this property. T is bigger than S.
T is bigger than S.
Yeah. Yeah. Yeah, T is bigger than S. So you might look at this result and say, well, it's obvious because, you know, if each vertex has degree S, then obviously the worst thing is to make them all the same, and then you get KST, and so you're just back to where you started. And right, so that's what this theorem is saying, that intuition is true, but it's not at all obvious how to prove it. Right? It's not at all obvious why sticking the neighborhoods together should be the hardest thing to find. In particular, the proof doesn't give it. Right? So if you think this is obvious, I encourage you to look for a different proof. That would be very interesting. Again. Okay. How are we going to do this? Yeah. Yeah, so let's say we apply, let's just like sketch for a bit. So we apply this lemma, and we find some large set A, such that every subset of some size has a large common neighborhood. How would we use this set A to find our graph H? Huh. So you'd like to find a large subset out here, such every subset has a large common neighbor in here. Right, so that doesn't seem like a crazy idea. In fact, it seems like a nice idea that might be useful in other situations. Here, you don't need to do it. So I just want to find H. Given this A, it's as big as you like, whatever, as big as you need. For whatever subset size you like, you've got a huge common neighborhood, as big as you need. Find me a copy of H. Where is H in this picture?
So X is on S. Mostly.
So I guess perhaps the clue is, because we're going to want to keep this set small. So S is actually going to have size S. Okay.
X is in NS.
Keep going and.
And for you. You choose one vertex from NS, and S will be the neighborhood.
Right. Right, so you want somehow, exactly, the neighborhood of whatever vertex to be this set. But this guy has a neighborhood of size S in Y. So the first thing you want to do is embed Y. Where do you want to put Y? We're going to find a copy of this graph over here. So I want to first choose where these vertices are. Where are you going to put these vertices? Inside A, exactly. Okay, so we're going to start by choosing a subset, a copy of Y here. Right, just arbitrarily. I'm just going to pick enough vertices so I have, and Y goes there. Right, so I've just put them in. I don't care where. Now I want to choose the vertices of X. So let's say the first vertex of X we come to. Vertex U. Vertex U has a neighborhood in Y. So we need to make sure that the corresponding, here's the corresponding neighborhood of U. Right? This is neighborhood in H, but now these vertices correspond to vertices in G. We need to make sure that X is chosen. It's not very good. X is chosen to be in the common neighborhood of these vertices. Right? So look at the common neighborhood of these vertices. We're going to make sure that U is chosen, in orange where it's chosen, U is put there. Does it make sense? So I'm embedding this H in this G, in this big graph G. First I chose where the vertices Y go. There's no restriction on Y. It's an independent set in H. Right? They can go anywhere. But we're going to put them inside A. And what's the advantage? Because then, when I come to a vertex of X, now there's a restriction. Now there's some edges that have to be present in G. So I have to pick this vertex in the common neighborhood of these guys. But these guys are now inside A, and they have size at most S, so they have a large common neighborhood. So I can pick U inside it. Does that make sense? So now let's prove an embedding lemma.
Sorry, bro.
Uh-huh.
They have size at most S, right? But your lemma is for size.
Yes. So tell me why that's okay.
Smaller intersection.
Bigger intersection, right?
Yeah.
Yeah. Smaller sets have bigger intersection. Exactly. Yeah. Okay. So okay, so embedding lemma says that you take this H, bipartite with this property. If there exists an A which is big and all S sets have large common neighborhood, then you can find H. So what are the conditions that you need for this argument? So this is H. H has these properties. Yes. No teorema. Is that right? Does that make sense? Okay. Does everyone understand the statement? So I want you to fill in what these two things are and prove it at the same time.
Same time.
Well, you know. By proving it, you will fill them in. Okay. So here is A. Let's embed Y inside A. And now let's suppose that we've already embedded some subset of X. And let's look at the next vertex U. So we've already embedded a bunch of vertices of X. We're going to embed the next one. Does it make sense? So I've embedded Y by just choosing where the vertices of Y go. I've embedded X prime by choosing where these vertices go. And okay, and there's going to be some edges here. And all of the edges that I needed in H are present in G. I don't want to embed the next one. So I take some U, let U be in X minus X prime. And let's look at the neighborhood. Let's let S is the neighborhood in H of U, which is a subset of Y. But Y has been embedded already, so I can think of S as being a subset of the vertices of G. Right? Now what do I know? I know that the neighborhood of the common neighbors of S, they're large. I'll draw them in blue. So here are the common neighbors of S. If anyone is colorblind in any color, then I apologize. Does that make sense? This is n of S. It's some set of vertices. Maybe intersects A, maybe intersects X prime, but whatever. And we know the neighborhood of S is at least something. how large would you like the neighborhood of S to be? Well, what do you want?
To choose a U which is not on X prime.
Exactly. You want to choose a U that's not in X prime and not in Y. So you want there to exist a U here. I'll do it in orange. Right, you want to embed U here somewhere. So how large do you want n of S to be?
Size of H.
Yeah, just number of vertices of H. Very good. And how large do we want A to be? Just size of Y, which, okay, let's say size of H is also good. Right? Approved. Yeah, so we just greedily pick each time, one by one. So we embed Y in A.
So X prime is a product of this grid of
We've just run this greedy algorithm at some point. How do you do the next step? You just do this, and you find a point. And there is a point because the common neighborhood of S is big enough, there's a point that you haven't already used. And you just continue until you've filled out X.
And then the U can be decided at Y.
No, the U must not be in Y and must not be in X prime. Otherwise, it's free. I mean, probably it shouldn't. I don't know, it doesn't matter about A because your neighborhood, your S is always inside Y. Okay. Yeah.
Can you do that lemma without considering the neighborhoods in A? I mean, doing like a partition, you understand?
So you want the neighborhood to be outside A.
Yeah.
I mean, it seems a bit more complicated because you haven't chosen A at the point at which you're doing these calculations. So yes, you have to be a bit careful because you don't really have very much control over that. There are various versions of the dependent random choice lemma, so I don't want to give you the idea that this is the only lemma of this form. Right? There are various different things you can do with different strengths and weaknesses. There's an excellent survey, perhaps I should mention before anything else happens, by Fox and Sudakov. I have the name somewhere. Anyway, Sudakov and Fox, where they give lots and lots of applications and other versions of this, which they need for certain applications.
But the idea is the same, right? To find a large subset
Such that the common neighborhoods have some property. Yeah, so maybe you don't want, so one variant would say not every pair has large common neighborhood, but most pairs have very large common neighborhood, that kind of thing. Right. Okay, so now let's finish the proof using this embedding lemma. So tell me what A, R, S, and T are.
A is the size of the vertices of H.
Yep. Very good.
R is the same.
Yep. S is S. Okay, let's see what T is. So n times the number of edges of our graph is over there. This is C of H times n to the minus 1 over S to the T. Minus n choose S, V of H over n to the T should be at least V of H. Okay, let's try to simplify this a bit. CH to the T, n to the 1 minus T over S, minus, right, so it's sufficient to prove we can replace this by something bigger, right? So we can replace this by n to the s if I want to. So we end up with v of h to the t times n to the s minus t. Right, I've just replaced this by something a bit bigger, n to the s. And so if we can prove this is true, this would imply this. Right? This is a slightly stronger inequality. OK, so what t would you like to choose so that this is true?
Maybe v equal s and a big constant.
Yeah, very good. So put t equal to s. This disappears. You get ch to the s minus vh to the s is at least v of h, which is true as long as c of h is basically bigger than v of h. Okay, 2v of h. That's it. Okay. Let's give another example. How about the Ramsey number of the hypercube? So first, what is a hypercube? So Q1, well, OK, Q0 is a vertex. Q1 is an edge. Q2 is a square. Q3 is a cube. Q4, I can just about draw. Two cubes joined with a matching. And then Q5 continues, right? It's a k-dimensional hypercube, a k-dimensional cube. So how many vertices does it have? Yeah. It has 2 to the k vertices. And how many edges does it have? What's the degree of a vertex in the hypercube? Yeah, so you're k vertices, k neighbors, sorry. Because you can think of the vertices as being 0, 1 to the k, and you differ if you differ in exactly one coordinate. Right? So it is k times 2 to the k minus 1, right? Okay, it's k regular. So the Ramsey number of Qk is saying, suppose you two-color the edges of the complete graph with n vertices. How many vertices do you need till you find a monochromatic copy of Qk? This was a problem that was well known for, well, I mean, still is very well known, but was wide open for a long time. That there were bounds by extremely clever and famous people of the form, like 2 to the 2 to the k, and 2 to the k cubed, things much bigger than this. But we can give a very short proof of 2 to the 3k. I think this is due to Fox, Conlon, and Sudakov. Maybe Fox and Sudakov and Conlon independently, or something. Yeah. They actually both proved something a bit stronger than this, but I'll talk about it afterwards. This is you give a short version. Okay. So tell me how to do this. that's an interesting idea. Yeah, so it's not a crazy idea that you split yourself in two, embed half it here, and then try and find a matching across. Turns out it's quite difficult to do. Because if you only find one copy of each, it's easy to kill it. You just don't find exactly that matching. So you need to find lots and lots and lots of copies, but then your induction is that you find lots and lots and lots of copies, and then you have to make sure enough of them survive, and yeah, so I don't know how to do that proof. Maybe that proof works, but gives some much bigger number. Yeah. So yeah, an extra property of this graph I didn't observe. What is the chromatic number of Qk? 2. Why? What's your coloring? Yeah, parity, right? Yeah, exactly. Yeah, so color sets of odd size red and sets of even size blue. Yeah, so another thing that I do regularly is think of sequences 0, 1 to the k and subsets of 1 up to k as being the same thing. Yeah, so apologies also if that's confusing. Okay, is that a hint? Why is the chromatic number being 2 good? Because it's bipartite, right? And we just proved a lemma that was about bipartite graphs. Maybe I should put the conditions here because I erased them, didn't I? I'll get rid of the proof and write the conditions instead. Okay. Yeah. So what are A, R, S, and T? Right, we're basically done, right? I mean, right? Yeah. Yeah, so remembering the proof, we'd even take it be 2 to the k minus 1, right? Because we only need to put half of the vertices in. Right, because the two classes have the same size. But yeah, whatever. R. Yeah, 2 to the k this time. Now we really need all the vertices. S. K. Okay, let's see what T is. So n times, how many edges does G have? What is G? I mean, if you take a clique, then you're definitely going to, you're definitely going to find a copy of H in it.
Oh, okay.
Right? one of the color classes. Which one do you want to take? Yeah, the one with more edges. So actually, it's even sillier. We're not even going to play the colors off against each other at all. Just going to take the bigger color class. Right? So n squared over 4 over n times 2, so a half to the t. Right? And just take the bigger color class. Minus n choose k times 2 to the k over n to the t should be at least 2 to the k minus 1. Now, what are we putting n to be? N is 2 to the 3k. So this is 2 to the 3k minus t minus, let's be a bit more careful this time. This is, no, perhaps I'm talking nonsense, but I don't need to be more careful. Yeah, so I'm being silly. N to the k, so 2 to the 3k squared, upper bound on this again, just n to the k. With an n to the t, so minus, okay, so plus kt, these guys, and then minus 3kt. Right, so minus 2kt. 2k to the k over n is 2 to the minus. So minus 2kt. Should be at least 2 to the k minus 1.
And you repeat that, please. Where did you get 3k squared?
N is 3k, and n is 2 to the 3k. And using n choose k is at most n to the k. And that's it. OK? OK, so what should t be? That seems like a reasonable choice. T is 2k, so 2 to the k minus 2 to the minus k squared is at least 2 to the k minus 1. And that's it. Yep. Yes. Right, so we're using both. OK, so let's write out the proof. So we did this calculation. Let's write out the proof. So let's take a 2 coloring of the edges of Kn and call the edge sets GR and GB. And let's suppose, without loss, that GR has at least as many edges as GB. Okay. Dependent random choice lemma applied to GR tells us that there exists a set A in the vertex set of our coloring, whatever, such that size of A is at least 2k minus 1, and the common neighborhood of S is at least 2 to the k for all subsets of A of size k. The embedding lemma that implies that Qk is contained in GL.
Now it's the size of A is at least 3 to the power A.
Yeah, so I guess Here I use the fact we only really needed a was at least y. Right. Yeah. Yeah. So I didn't really use it. It just allows us to take t as 2k rather than 2k minus 1 or something. Right, if you just change t slightly, then this gets bigger. Yeah. I mean, in fact, you'll notice that this was not sharp, right? There was a lot of slack here. We could have taken t to be quite a bit smaller, and therefore we didn't really need n to be quite as big. So what it actually gives is something a bit closer to 2 to the 2k. OK, to get to 2 to the 2k, then you need to work harder. So the result of Fox and Sudakov and also Conlon is really a polynomial times 2 to the 2k. So that's actually the best known current upper bound. Yeah. Did it make sense? Everyone happy? So how close to best possible is this? What do you conjecture the answer is? What's the best lower bound you can prove? OK, I can prove it's at least 2 to the k. Who can beat 2 to the k? If you've got fewer, there aren't enough vertices. Yeah. Yeah. Yeah, so beat 2 to the k. You can beat 2 to the k, right? You can prove 2 to the k plus 1 or something stupid. I mean, OK, let's prove 2 to the k plus 1, and then you'll see what I mean to generalize it. Give me a coloring on 2 to the k plus 1. I don't mean 2 to the k plus 1. I mean 2 to the k plus 1 vertices. That does not contain, oh, sorry, even 2 to the k, sorry, 2 to the k vertices. Show that 2 to the k is not enough. It's a stupid coloring. Come on. So tell me. Don't be shy. Yeah, exactly. There you go. Have I got any red and blue? While I'm looking for red, you can tell me how to generalize it. There's no red. Orange and blue.
You have 2 to the k.
Yeah, 2 to the k minus 1 vertices here. And 1 vertex there. OK, now, yeah, keep adding vertices, right? At what point do you fail?
When you have 2 to the k minus 1 in the other potato.
Yeah, so can you go that far? Sorry? Can you go that far? No, you can find it across, right? So, how far can you go?
Maybe 2 to the k minus 1.
Yeah. That looks good, isn't it? 2 to the k minus 1 minus 1. Now, anything that uses red, I mean, you have to put one of the classes inside here, right? Is it true? Seems likely. Anyway, so I think this gives 3 over 2 times, like some constant times 2 to the k. I don't think anything better than this is known, or whatever the correct thing is, if this is wrong. So conjecture. I think this is all conjecture of Erdös. Most things are. This should be big O of 2 to the k. Right. You should really, once you have 100 times the number of vertices you need, that should be enough to find the hypercube. It seems to be extremely difficult. This is one of my favorite open problems in Ramsey theory, in graph Ramsey theory. Right. Okay, maybe we'll just start for one more. Maybe I'll send you another list just with some applications of dependent random choice, maybe a couple other things on. Nothing for, you don't have to hand them in or anything, just because I might put some things on the exam, so just give you some practice. Right. Yeah. So I'll probably put one of the things I did today on the exam. Probably. Right. What do I want to do?
When we will send?
When what, sorry?
When we will send?
The lister?
Yeah.
Maybe I'll try and send tonight. Just so you can, some more practice. So the second lister was quite a lot harder than the first one, so don't worry if you can't do them all. It's just to give you some fun and help you to think. Yeah, maybe on, I'm not quite sure, on Friday or Monday, would you like to have a class of going over old stuff? Okay, maybe we'll do that then, rather than do more stuff. The alternative is I could do some non-examinable fun stuff, but it's up to you. Okay, so maybe have a think and tell me on Friday. Okay, so how do I want to write this? So, okay, maybe I'll write it like that. So what's a topological copy of H? So I think I mentioned this at some point. So if this is H, a topological copy is just one where you add in vertices along the paths. So to the edges and the paths. Sorry. So here is a topological copy of this triangle with an edge. So a topological copy is obtained from this clique by adding vertices along the edges. So it says the graph of positive density contains this huge topological clique of size delta n.
Delta depends on
Epsilon, yeah. Yeah.
I have a question.
Mm-hmm.
If I put a triangle inside the triangle, is it topological?
A triangle inside a triangle. No. So every topological triangle is a cycle.
No, these vertices you add,
Yeah.
connect them inside with the other edges. Yes.
No, definitely not allowed.
No?
No. You add vertices, you don't add edges.
Sorry,
Yeah.
what was his question?
Is whether you're allowed to add extra edges in between these things that weren't there before. And the answer is no. Because that would be topologically different, right? I mean, the point of this is putting these vertices on doesn't change the topology of the graph.
Because I thought that you could slide that to
You could slide
the original edge.
the original edge, like this
The
one.
original vertex.
You can.
So it would be the same.
As what?
So you can have
This one. Yeah, so the original edges have to stay in place. They can only move in a way that's whatever, topologically equivalent. So the thing, but basically the idea is if you remove all the vertices, including the ones that were there in the first place, you end up with some sort of loop in space, right? And your final thing should be topologically equivalent to that. So you can wave it around and then stick vertices on any way you like, but you end up with the same sort of structure.
Just to make sure.
Yeah.
If you add an edge, the same edge you draw there, and you call that G, you still have H inside topologically there, right?
Sorry. If you cut this one,
No, add an edge.
add an edge.
The same edge you draw.
Oh, this one.
Yeah.
Uh-huh.
You still have H.
Oh,
inside.
sorry. If you find this bigger thing, then that's fine. Because you erase it and you found your,
Okay, so
yeah.
you are allowed to erase edges.
Yeah, sorry. By exists, I mean as a subgraph. Yeah, sorry. I meant the thing with the extra edge is not a topological copy of the original thing. It's a bigger graph. Yeah, but we just want to find it as a subgraph. Yeah, sorry. So we don't want to find an induced copy. Yeah. Okay. Sorry. Thank you. Okay. So this was another old problem of Erdős, solved by some subset of Fox, Conlon, Sudakov. They solved a whole bunch of problems with this method. It's quite impressive. They just went around bashing old problems on the head. I should perhaps say something about the history. So this method, it kind of emerged in the 90s out of work of Kostochka and Rödl and independently Gowers, working on totally different things. And then this was discovered by Sudakov, and then ALON and correlated Sudakov proved a bunch of stuff with it. And then Sudakov and Fox and Conlon went off and proved a whole bunch of other stuff with it. So it was really sort of popularized and developed by Conlon, Fox, and Sudakov, but the origins are in some sort of, not quite the same form. There's versions that were earlier. So this is sort of a method that sort of emerged out of the subject. Right. Sorry. So what's the proof of this? Any ideas? Here's your clique. What does your topological copy of it look like? It's supposed to be something that's easy to find, right? We can find in this graph using these techniques. And it's got to be of size delta times root n, right? And the vertices that you add on the paths have to be different. You're not allowed to use the same vertex on different edges. So on average, how many vertices can you have on each edge? I mean, how many edges are there of this clique? It's of size delta root n. So delta root n, choose 2, it's like delta squared times n. You've only got n vertices overall, so you can only add a constant number of vertices on each path. So you're not going to connect them by very long paths. So let's connect them by short paths. What's a good length of path? To connect things by 2. Why is 2 a very good length of path to choose? What can you tell me about this graph? What is a very useful property this has? Bipartite, exactly. right? Very useful property. Okay, so what are you going to do? You have 10 whole minutes. It shouldn't take that long. Okay, as soon as you solve this, then we can finish.
Since you are erasing that, I think we can use the
Yeah, let's use random choice. So what do we want? We want to use the random choice and an embedding lemma. So what do we know about this bipartite graph? So it's got a vertex at x union y. What can you tell me about the degrees in x? And how large are x and y? Let's maybe call it the number of vertices. The original thing is k. And we'll just figure out what k is. So the white ones are one class, the orange ones the other. So x equals y equals k. And what's the degree in H? H is the subdivided graph. So the one so H is this. Sorry? X is either the orange ones or the white ones. You get to choose.
If we take the white ones, it's k minus 1, 0 minus 1,
2. So yeah, let's take 2. Sounds like a good idea. Okay, so what are these guys going to be? K. 2k. 2. N times number of edges of our graph is epsilon n squared. Times epsilon to the t. Minus n choose 2 times 2k over n to the t should be at least k. What should t be to get the best possible k? You want k to be as large as possible. I mean, and I've told you what it's going to be, right? So.
I'm sorry, why is R 2K?
Ah, sorry, I'm an idiot. Thank you very much. I'm an idiot. This is nonsense. No one pointed it out. Why is it nonsense? How large is x and how large is y? Sorry? Yeah. X is k choose 2. Thank you. Much better. Right, so what should these things be now? A is, this has to be y, so this one is still k. But R has to be k choose 2 plus k. So k choose 2 plus k. Right? So now, yeah, it's really useful that we have this stronger version where we put y. Okay. So this is at most n. So this thing had better be less than n squared. So k choose 2 plus k better be less than n. How small do you want to make this? Well, it's also going to be smaller than epsilon to the t, right? So this had better be smaller than epsilon. And then how large should t be? Well, k is like root n. So this can be like root n. So we pick t such that epsilon to the t is roughly root n. And if k choose 2 plus k over n is at most, so I guess it should be epsilon squared, not epsilon cubed, epsilon to the 4 or something. Let's make it epsilon to the 4. Right? If you pick t and epsilon such that, and k such that this is true, epsilon's given, right? This implies that this whole thing is root n minus, this would be epsilon to the 4t, which is 1 over n squared. 1 over this. Thank you. Right. So this would be minus a half or something. Should be at least k. K here is roughly what? Is like epsilon squared root n. Which is true. So we proved epsilon squared root n. It's okay? Okay. So as you can see, this method does a whole bunch of different stuff. Whenever you want to look for some kind of subgraph, whether it's a small subgraph, whether it's a huge subgraph, it's an incredibly useful technique.
So I didn't get the strategy. This new variable k, why did you add it?
I just didn't want to, write delta root n everywhere.
Okay.
I want to see that you could just write down k. K is what you're trying to find. You can just make k as big as possible. Just to see immediately what, rather than writing delta root n choose 2 plus delta root n, you can see immediately what k has to be, right? To make it work. Okay, right. So have a think before Friday whether there's particular things in the course you want to go over, problems for the example sheet, whatever you want to do. If people don't have suggestions, or if we run out of suggestions and have more time, then I'll start on some non-examinable fun stuff.